Okay, so before we start transforming curves, we need to know three core graphs. The first two you already know, the quadratic, so I'm going to whiz through this, passes through the origin. The second one, y equals x cubed, again looks like so, passes through the origin. This point that I'm indicating here is called a point of inflection, which you'll learn more about later in the course. But the graph that most students don't know when they come in is the reciprocal graph. That's y equals 1 over x, which looks something like this. Now, a few things to notice about the curve. This curve part here will never ever touch the y-axis here, just like this curve will not touch the x-axis here, and vice versa over here. So to depict that, what we do is we use these dotted lines, which are called asymptotes. So an asymptote means the graph will never cross or touch that line. So you can see we have one at x equals 0 and y equals 0. So when we're transforming this graph, the asymptotes need to move with it. And it makes sense why this graph here doesn't touch the y-axis, because here at the y-axis x is equal 0 and we can't divide by 0. So that makes sense. And similarly, this goes on forever, because as x gets really large, let's say 1 over a million, y gets infinitesimally small, but I can never make this y equal to 0. So now we can start talking about our transformation rules and what these rules do to our original graphs. So the reason we use transformations is so that we can very quickly sketch our original graphs in a different way. So let's say, for example, we had a scientific experiment and we mapped out graphically what happened in that experiment. Let's say we wanted to change a parameter then, which essentially maybe doubled something. We could essentially then, using our rules of transformations, very quickly draw what that graph would look like without having to plot individual points beforehand before we could sketch it. Also with transformations, I could then rewrite the new equation of that curve very, very quickly using the rules without having to do the algebra from base. So we need to discuss what these transformations are. So this group here, this group affects the y-axis. So these are y-axis transformations, otherwise known as outside transformations. This group down here, this is our x-axis transformations. So these things affect the x-axis. Right, so you see, these are called outside transformations because we have our A outside this f of x. The x-axis transformations, you can see that A is within, all these things are within the brackets, so within the f of x. Okay? Okay, so let's start defining what these things actually mean in reality and how we could write them down and how they're going to help us. So this first rule here, f of x plus a, this means the graph will move up the y-axis by a units. So what that means is, or what you guys really need to just write, is that there has been a translation by vector 0a, and this is assuming that a is of course positive. Okay, so this means here that the graph has no change in the x-axis, and that makes sense because we're talking about y-axis transformations, and that the graph has moved upwards by a units. Similarly, we can say exactly the same thing about f of x minus a, that the graph will move down the y-axis by a. So for us, we would then write in an exam, because in the exam this is what counts. A translation, that's 1 mark, and then the actual vector 0 minus a is the second mark. We then need to look at this next rule, a f of x. Don't worry, we're going to actually put these in practice in a minute, but a times f of x. So this means the graph has been stretched parallel to the y-axis by a scale factor a. So what this means is that every single y coordinate has been times by a. And you'll see then that that means the graph has been elongated if a is above 1, or if a is, say, a half, the graph will be compressed downwards. And finally, this rule minus f of x means that the graph has been reflected in the x-axis. So it has been reflected, all the y values have been multiplied by -1. So you can see that actually this rule here is the same as this with a equals -1. Then we'll start talking about the x-axis transformations. So let's write these rules here. So for this first one, f of x plus a means the graph has moved a to the left along the x-axis. Okay? So for you guys, what you guys need to write is a translation by minus a 0. So you see, this is contrary to what you think it should be. This x plus a, you would think, oh right, it must move to the right, but actually it's the other way around. It moves to the left. Okay, so this is minus a and 0, your transformation. Minus a along the left of the x-axis, no effect in the y-axis. So similarly, this f of x minus a, the graph has been translated or moved by a towards the right hand side along the x-axis. So for you guys, again, we need to say that there has been a translation by a and 0. So you see again, you'd think, oh, it goes to the left, but actually it goes to the right. This next rule here, f of ax, this means that the graph has been stretched parallel to the x-axis by a scale factor 1 divided by a. So 1 divided by a. So be very careful with this, okay? Because the scale factor is not a anymore. It's 1 divided by a. This is why it's different to our one up here, okay? So the scale factor is 1 divided by a. And that is what you need to write in an exam. So if a was 2, the scale factor would be a half, which means all the x coordinates will be halved. And finally, this graph here, the transformation here, f of minus x, the graph has been reflected in the y-axis this time, and that would be all you need to write. The graph has been reflected in the y-axis, and again you can see that actually this minus is this one here with a equals minus 1. So let's see these things in action then. So let's see how these things are actually applied to our original graph, y equals x squared. If we let y equals f of x, then I can say f of x equals x squared. Let me show you the first rule in action. So f of x plus a, where, as you can see up here, we're going to say a equals 2. So actually our new transformation is f of x plus 2. So our original graph, let's say f of x equals x squared, looks like this. I'm going to apply my transformation f of x plus 2. And remember, from our rules, this is a translation of the graph 0, 2, which means the whole graph moves up by 2 units. So at the moment this is at the origin, and this goes up by 2 units. So here y equals 2. First rule, done. Let's now try the second rule. So again, original f of x equals x squared. My new rule, we're going to have f of x minus a. So again, let a equal 2 from our example. Have a graph, the original graph like this. And in our transformation, the whole thing is moved down by vector 0, minus 2. So this is actually now at minus 2. You see? Let's keep going. So that's that one. Now we're going to look at my f of x equals x squared with the transformation af of x, where a equals 2. So original, we have like this. So if we pick a point, here is 0, if we pick this point 1, the y value at 1 will be 1, won't it? But now with our new transformation, we have 2f of x, so this means all the y values will be times by 2. So my graph is essentially stretched upwards. And we can see that's the case. So if we look again at our x equals 1, we have, instead of y equals 1 corresponding, it's going to be y equals 2. So the graph has been elongated upwards. So if I was to draw it on my original graph, my new graph would stretch up like this. Okay? So let's then look at our final y transformation. So again, we'll take our original f of x equals x squared. And now we're looking at our new rule, which is minus f of x. So the original looked like so. And with this minus f of x, remember, all the y values are times by minus 1. So, and it's reflected about the x-axis. So actually it's just flipped upside down like so. And there we go. There are the y transformations in practice.